Okay, Precalc C, here we go. We're going to go over sequences in series packets, pages 19 through 22. And these problems are all a little bit hard in sort of different kinds of ways. So let's do it. Use induction to prove that 18 to the n minus 1 is a multiple of 17. Whoa, this sounds hard. Okay, well, let's check it out. So let's just kind of play around and see if we get it. When n equals 1, what is 18 to the n minus 1? Well, that's just 18 to the 1 minus 1, that's just 17. And so it appears that 17 does go evenly into 18 to the 1 minus 1. So far so good. Okay, let's check n equals 2, just for some feeling of, I don't know, comfort or something. What about 18 squared minus 1? Can I do 18 squared in my head? Yeah, I probably can. That's 9 times 2 times 9 times 2, so that's 81 times 4, so that's 324. I think I just knew that one. So this is 323. All right, now I personally do not know my... Is that right? I personally do not... Oh yeah. Do not know my 17's times tables, but if I add 17 to this, then I get 340. And 340 is 34 times 10, or 17 times 2 times 10. So 340 is 17 times 20. This must be 17 times 19. That's like probably right. 190 and 70, that's 260 and 63, yep. Okay, so it appears that 17 also is a factor of, or goes evenly into, or divides 18 squared minus 1. Okay, but now that's enough of that. I need to now prove this kind of in general. So, okay, well, we do it by induction. So let's just make my inductive hypothesis. I've sort of already done the base case. In fact, I've done 2 of them. So my inductive hypothesis is that I assume that 18 to the k minus 1 is a, well, I might as well write it out using my preferred notation, which is that 17 divides 18 to the k minus 1 for some k greater than or equal to 1. Okay, so I'm going to take an arbitrary number k, and I'm going to suppose that the thing I'm trying to prove is true. And, okay, if you don't like this divides notation, you don't have to use it. You can just write out, is a multiple of. But anyway, what I need to prove is that the next number, in other words, 18 to the k plus 1 minus 1, also is a multiple of 17. Okay, if I can show that whenever 18 to the k minus 1 is a multiple of 17, that 18 to the k plus 1 minus 1 is a multiple of 17, then since it's true for 1, it must be true for 2, and since it's true for 2, it must be true for 3, and then that will show that it's true for all numbers. Okay, so that's my plan. Now I just have to do it. And so, okay, we just start. We just start with 18 to the k plus 1 minus 1, and we just somehow try to show that it is a multiple of 17. And, there's one important thing that I am going to use. I am going to use this fact. I am going to use that 18 to the k minus 1 is a multiple of 17. It is my inductive hypothesis. It's the one thing I know. So I somehow have to use this one thing I know, that 18 to the k minus 1 is a multiple of 17, to show that 18 to the k plus 1 minus 1 is a multiple of 17. Alright, well, let's make this look as much like the thing that I know as possible. So, of course, one thing we can do is just write this as 18 times 18 to the k plus 1 minus 1. Okay, and you have to be sort of careful with your, order of operations here, because, we multiply first, and sort of then we subtract. Okay, so what's kind of going on here? This requires sort of one smart little thing that, oh no, sorry. That's what I meant to say. We need to do one kind of smart little thing now. And here is the little thing. Okay, what I know is that 18 to the k minus 1 is a multiple of 17. So, okay, there's a couple different approaches here. Yeah, I guess the thing to do is to just say, okay, well then, what does that tell me about 18 to the k? 18 to the k is therefore 1 more than a multiple of 17. I'm just going to kind of write this off to the side. This is my thinking on the side, is that 18 to the k is a multiple of 17, plus 1. And in fact, if you even want to, probably the easiest for beginners or something way to do this problem is to off to the side, I'll just put this in a circle because this is my sort of side thoughts. Just even state this even more clearly, right? My inductive hypothesis is that 18 to the k minus 1 is a multiple of 17. So what do I know? I know that 18 to the k minus 1 is like, I don't know, 17m, for some m. That's just what it means to be a multiple of 17. Well, if 18 to the k minus 1 is a multiple of 17, then what can I say about 18 to the k? It's just 17m plus 1. So this is just written out now in maybe clear algebra. This is what I just said over here kind of verbally. And one thing you could just do is just plug in 17m plus 1 right now for 18k, and then this whole problem just is over. Alternatively, you can do something maybe a little bit more fancy, which is you can say, okay, well, let me just rewrite this 18 to the k as 18 to the k minus 1 plus 1. And why would you do something kind of weird like that? Of course, this is just valid. It's because 18 to the k minus 1 is the only thing I know about, and so I'm sort of making my expression look like that as much as I can. In other words, what is this? This is 18 times 18 to the k minus 1 plus 18. So I'm just now distributing this 18 through. If you want to be even more kind of clear about this, I'm just choosing, inspired by my knowledge of 18 to the k minus 1, I'm choosing to express 18 to the k as 18 to the k minus 1 plus 1. And then sort of grouping these two together, now distributing the 18 through, and then of course there's still this minus 1 just chilling here. Okay, well now do you see that we are just done? Because we have 18 times 18 to the k minus 1 plus 17. And this is, by assumption, a multiple of 17. So now you say something like, by inductive hypothesis, this must look like 18 times, 17p or something like that. I might as well just use m. It's the same thing I use over there. Plus 17. And so we just have shown that this is a multiple of 17. Okay, so what do we know? We know that 7 divides 18 to the 1 minus 1. And what we proved is that if 17 divides 18 to the k minus 1, then 17 divides 18 to the k plus 1 minus 1 for any k greater than or equal to 1. So, by the principle of mathematical induction, 17 divides 18 to the n minus 1 for all n. For all n. Okay, I just want to say maybe a little bit more about what happened over here, because this was the sort of crucial moment. Was this step right here, and it seems that you had to be so smart or something to think of this. But the sort of more kid-friendly way, arguably, to do this problem. This is how I think of it. But maybe the more kid-friendly way is really to do kind of just what I said over there, right? Which is, so I'm just now going to sort of show a kind of alternate solution to this problem that you might prefer, which is writing this as taking it from this step, right? Just like that. I can just stick in right here, since I know that by my inductive hypothesis, 18 to the k minus 1 is 17m, then I can just stick in place of that 18 to the k, I can just put in 17m plus 1. And that might somehow feel more like a real solution to you. You might sort of feel kind of better about that. And then when you distribute through, of course, you get 18 times 17m plus 18 minus 1. So it's really just the exact same, thing. It's just kind of cosmetically different, whether you choose to, because now we're already here. So I'll put like a kind of a blue box around this, because you might sort of prefer that instead of what I did. So whichever one, whether you want to just rewrite this as minus 1 plus 1, or you want to sort of use the fact that you know, write it out algebraically. I guess this is kind of easier. And then kind of solve for 18 to the k and stick it into the expression that I'm investigating, and then it all just kind of falls out. Okay, hopefully that was okay. All right, one down, like bunch to go. Bunch to go. Okay, shot. Yeah. Next, number 52. 52, man, what a packet. 52. Use induction to prove that n times n squared plus 5 is a multiple of 6. N times n squared plus 5 is a multiple of 6. Okay, how are we going to do this? Well, let's just check it. How about when n is 1? Well, when n is 1, you get 1 times 1 squared plus 5. Well, that's 1 times 6, so that's just 6, so it works. Alright, how about when n is 2? Well, when n is 2, I get 2 times 2 squared plus 5. So that's 9 times 2, that's 18. It seems to also be true. Alright, so I'm feeling like this is true. How can I prove it? Well, it's the same thing. I make my inductive hypothesis. Let's assume that 6 divides k times k squared plus 5 for some k greater than or equal to 1. Okay, so take an arbitrary k and suppose that the relationship that we want holds. And now, to complete the inductive step, I just need to show that it stays true for the next number. So I need to show that 6 also goes evenly into, we've got to be a little bit careful here, k plus 1 times k plus 1 squared plus 5. This is why I like to use a different variable, because we're substituting in k plus 1 for n. Okay, so how am I going to do this? Well, alright, I guess I'm just going to start. I'm going to start with k plus 1 times k plus 1 squared plus 5, and somehow from this I need to show that it's a multiple of 6, which is not obvious at all. And the one big fact that I am of course going to use is that one. Okay, well, what should we do? I have no idea. Let's just multiply. I think I just multiply everything out and just kind of see what happens, right? Now let's do it. So, okay, we begin. This is k plus 1. What's inside here? Well, that's k squared plus 2k plus 1 plus 5. So that's k plus 1 times k squared plus 2k plus 6. And I don't see any real thing to do here that's deep or cool or anything. except to multiply everything out. So let's go. What do we get? We get k cubed plus 2k squared plus 6k, and then plus another k squared plus 2k plus 6. Okay, so this turns out to be k cubed plus 3k squared plus 8k plus 6. Alright, well, I got something now. Why is that a multiple of 6? I have no idea. But what do I know? What is the one thing that I know? Well, the one thing that I know is that k cubed plus 5k is a multiple of 6. Well, if I know that k cubed plus 5k is a multiple of 6, then I should try to find k cubed plus 5k inside of this. In other words, let me write this as k cubed plus 5k plus, what's left over? 3k squared plus, I took 5 of the k, so that's 3k plus 6. Okay, so hopefully that was pretty clear. I just split up 8k into 5k and 3k, and put the 5k over here with the k cubed, and put the 3k over here. Why would I do such a thing? Because by my inductive hypothesis, I now know that k cubed plus 5k is a multiple of 6. So I'm just going to call this like 6m. And now the only thing that's left over to do is to show that that's a multiple of 6. Well, is it? Hard to say. Let's just use kind of factoring techniques and see what this even is. If I factor out a 3, I get k squared let me do something even smarter, because, you know, what's kind of staring me right in the face here is that one of my terms is just a 6. So actually, the sort of super smart thing to do is to just leave that 6 out there, because, you know, 6 is just 6. So actually, this whole thing just boils down to, can I show that 3k squared plus 3k is a multiple of 6? And I think it just is. Because out of this 3k squared plus 3k, I can factor 3k and k plus 1. Okay, so the k cubed plus 5k part is a multiple of 6. 6 is, of course, a multiple of 6. What does it take to show that that's a multiple of 6? Well, it's already a multiple of 3. So this whole problem is done as long as k times k plus 1 is even. Is k times k plus 1 always even? Yes. Because k is either even or odd. If k is even, then we're done. And if k is odd, then k plus 1 is even. So I'm just going to write over here, like on the side or something, you know, fact. K times k plus 1 is even. Reason? Well, it's just, okay, this isn't even worth writing down, it's just so clear, right? If k is even, then the product of an even and anything is even, and if k is odd, then one more than an odd is even, and so one of these two has to be even. A simpler way of putting it is, if you give me two consecutive numbers, their product must always be even, because precisely one of them is even and one of them is odd. Okay, and so without writing any more things down there, I'm just going to say that this k times k plus 1 is guaranteed to be even. And if that's guaranteed to be even, then we can write it as, I don't know, like maybe like 2p or something like that. And now we are really done, because this is just 6 times m plus p plus 1. And so that is a multiple of 6. And so 6 does divide k plus 1 times k plus 1 squared plus 5. Whew. This is like some discrete math here. Okay, and now we say, so since 1 times 1 squared plus 5 is a multiple of 6, and whenever 6 divides k times k squared plus 5, I can prove from that that 6 divides k plus 1 times k plus 1 squared plus 5, I'm just making my closing remark now, that if this is true for 1, and whenever it's true for a number, it's true for the next number, then by the principle of mathematical induction, 6 divides n times n squared plus 5 for all n greater than or equal to 1. Okay, so that was number 52. I think I will stop now. Okay, we're back for page 20. This is number 53. This is another proof by induction. The theorem is prove that the sum of the cubes of any 3 consecutive integers is a multiple of 9. Okay, so what we need to prove is that if you take a number, a cube of a number, a cube of the next number, and a cube of the number after that, then what you get is always a multiple of 9. So, in other words, we need to prove that n cubed plus n plus 1 cubed plus n plus 2 cubed is always a multiple of 9. So prove that 9 goes evenly into 9 cubed plus n plus 1 cubed plus n plus 2 cubed. Okay, maybe in this case it does kind of make sense to give this thing a quick nickname. I don't know if that's helpful or not, but I don't feel like writing this over and over again, so let's just call this a sub n. So let a sub n be the sum of n cubed, n plus 1 cubed, and n plus 2 cubed. So now we can just check this. What is a1, for example? Well, a1 is just going to be 1 cubed plus 2 cubed plus 3 cubed. And that's not obviously a multiple of 9. But, okay, we can just do it. 2 cubed is 8, 1 cubed is 1, 3 cubed is 27. So that's 1 plus 8 plus 27. And that's 36. And so it is true that 9 divides 36, so 9 divides a1. Okay, just so I really believe it deep down, we can see what is a2. Well, a2 is just 2 cubed plus 3 cubed plus 4 cubed. And actually, well, okay, cool. So what happens when you do this? Well, you get 8 plus 27 plus 64. What's that? 35 and 64 is 99. I believe that's right. So, 11 and 80, 91 and 8 is 99. Okay, and so indeed 9 also divides a2. So I'm feeling like this is just true. Okay, cool. Let's prove it by induction. And then maybe I'll mention how you could prove this, not by induction. Okay, the thing about proof by induction is you don't really need to have a good, deep understanding of what's going on to do it. All you do is you make your inductive hypothesis. I'm going to put this down. Inductive hypothesis, assume that 9 divides a sub k for some k greater than or equal to 1, and then what I need to do is just show that 9 divides a sub k plus 1. Okay, so I'm not sure how much this abbreviation is really helping me, because I'm now just going to turn around and kind of write it out long style. What do I know? What I know is that that when I take k cubed plus k plus 1 cubed plus k plus 2 cubed, what I know about that is it's a multiple of 9. Is a multiple of 9. And what I need to show is that when this is true, this becomes true of the next number. So that k plus 1 cubed plus k plus 2 cubed plus k plus 3 cubed is a multiple of 9. Okay, Let's get going. I'm going to put a box around this big fact that I know somehow, which is going to get used. And the thing is, the very thing that I am trying to show is a multiple of 9 is actually just quite similar to the thing that I know. What I mean by that is, and this whole problem is just maybe a little bit kind of silly because it's really not that hard once you understand the setup. So I'm going to take k plus 1 cubed plus k plus 2 cubed plus k plus 3 cubed, and my goal is show that this is a multiple of 9. Alright, well, let's specifically expand out k plus 3 cubed. What is k plus 3 cubed? Well, I know how to do this kind of thing now, right? It's going to be k cubed plus 3 times k squared times another 3. I'm doing the binomial theorem now. Plus 3 times k times 3 squared plus 27. Okay, so maybe you could just do that in one step in your head, but using the binomial theorem, yeah, I always know, that's like kind of a cubed plus 3a squared b plus 3ab squared plus b cubed. Okay, and yeah. So look, I'm just kind of done now, right? Because all of this just is the thing that I already know is a multiple of 9 by my inductive hypothesis. By the inductive hypothesis, after expanding out that third term, this is a multiple of 9, is a multiple of 9. And so the only thing I need to show is a multiple of 9 is the rest, and it just is. So, okay, so here we go. By my inductive hypothesis, this whole thing is like 9m. And what is all this? Well, I can factor a 9 out of it, and I see... no, I guess I don't quite get a 9 just yet. Sorry, I was a little bit too hasty. What is this? This is, oh no, yeah. I'll just write it out one more time. What is this? It's 9k squared plus 27k plus 27. So yeah, it's totally multiple of 9. So it's 9k squared plus 3k plus 3, and well, there we go. I have just showed that this really is m plus k squared plus 3k plus 3. And so 9 does divide a sub k plus 1. Okay, so that's just kind of straightforward, basically, proof by induction. Is it possible that you don't even need to prove this problem by induction? I haven't planned this out in advance or anything, but while I was looking at this, it just seems like this is just going to be, well, you know what, I'll just stop there. Okay, good. Okay, that was page 20. Let's do 2 more problems, pages 21 and 22. Let's kind of just do it, maybe? This next problem, I think, is very exciting. Page 21, number 54. Sha. Okay, here is what we are given. We are given a particular recursive sequence. The first term we're told is 1/2, and the nth term is the previous term minus the previous term over n plus 1. Okay, so this is a recursive formula. Alright, what can we do with this recursive formula? Well, step 1 is write out the first few terms of the sequence, find the pattern, and make a conjecture for a formula in terms of n for the nth term, then prove your conjecture using induction. Okay. Yeah. Good. So first of all, this is just begging to be simplified. What do I know about a sub n? Well, it's a sub n minus 1, so it's the previous term minus the previous term over n plus 1. So if I factor out the previous term, then I'm left with 1 minus 1 over n plus 1, which is, well, this can be simplified as well, right? This is a sub n minus 1 times, getting a common denominator here, that's n plus 1 minus 1 over n plus 1. And so I have a kind of a better maybe formula, a little bit more succinct than the one that was given to me, which is that the nth term is just always going to be the previous term times n over n plus 1. Okay, so great. I still have some work to do, because the overall goal of this problem essentially is to convert this recursive formula into an explicit formula and to prove that it is correct. Okay, well, we begin with the directions, which are to write out the first few terms of the sequence. That's a little bit vague. So okay, we'll do as many as we need to do to see the pattern. So the first term is a half. What is the second term? Well, it's going to be 1/2 times, n is 2 now, so that's going to be 2 over 3. So it's 1/2 times 2/3, so that's 1/3. And what is the third term? Well, the third term is going to be 1/3 times 3 over 3 plus 1, so that's times 3/4, so that's going to be 1/4. Okay, I think I basically get it now. It seems that, so here is my conjecture. My conjecture is that the nth term is just 1 over n plus 1. Seems like the first term is 1 over 2, the second term is 1 over 3, the third term is 1 over 4. So that's a pretty easy pattern to spot. So that's what I got. Okay, so I think the hardest part of this problem is just kind of remembering sort of what's going on, right? So what is going on? I've been given, here's what I know about this sequence. Kind of by definition, this sequence is defined so that the first term is a half, and subsequent terms are like the nth term is the previous term times n over n plus 1. So okay, I chose to simplify this a little bit more, but even if you didn't do that, it doesn't really change anything. This is by definition my sequence. But now I have a sort of claim. My claim is that I stumbled upon down here by pattern recognition. My claim is that in fact the nth term is just 1 over n plus 1. Okay, and so I'm going to prove this by induction. And alright, the base case is already done because we've already seen that it works when a is 1 and etc. when a is 2. So now I'm going to make my inductive hypothesis. And so, alright, what's my inductive hypothesis? I shall assume for arbitrary k that the formula for the kth term is 1 over k plus 1. And what I need to do is I need to show that a sub k plus 1 is 1 over k plus 1, plus 1, otherwise known as 1 over k plus 2. Okay, so the algebra here is easy. What's hard is like the logic of it all. What is really going on here? What's really going on here is that this sequence has been defined recursively. But I think that I have discovered an explicit formula. And I think that the explicit formula for it is the thing on the right. So on the right we have kind of just an algebraic expression. On the left we have this sequence which has been defined recursively. Okay, and now I'm going to prove that this is true, and I'm going to prove that this is true by induction. So I assume that 1 over k plus 1 is the correct formula for the kth term of this recursive sequence. And I'm going to show that if it's true, then it's true for the next term. Okay, so now, and this is the part that's maybe kind of subtle, how am I going to show this? Well, I have to take the k plus first term, and what do I know about the k plus first term? Well, by the definition of this sequence, the only thing I know about the sequence is how to generate a term from the previous term, recursively. In other words, what is the k plus first term really? Sort of by definition, the k plus first term is, well, I reach for the definition of the sequence. The definition of the sequence is recursive. And so it's going to be, stick k plus 1 in for n here, and you get, well, it's the previous term, ak, times k plus 1 over k plus 2. Okay, good. Maybe I'll even just write, sort of by definition of a sub k plus 1. By the definition of this of the sequence. Okay, well, now I use my inductive hypothesis. Because my inductive hypothesis is that 1 over k plus 1 is the correct formula. So I substitute 1 over k plus 1 here. Why am I permitted to do that? I'm permitted to do that because my assumption in this proof by induction, based on this inductive hypothesis, my assumption is that these two are the same, and I'm using that assumption. Okay, well, look, now we're just done, right? Because multiply these through, and what do you get? You get 1 over k plus 2, and that was exactly what we were trying to show. And so this whole thing is just over now. Okay, so sort of blink and you miss it. Okay, and well, let's just wrap it up. What have we shown? We've shown that the first term of this sequence is 1 over 1 plus 1. And we've showed that if you assume that the kth term can be expressed explicitly as 1 over k plus 1, if that's true, then the k plus first term of the sequence can be expressed recursively as 1 over k plus 1 for any k greater than or equal to 1. In other words, whenever this is the correct explicit formula for the kth term of this sequence, then this is the correct explicit formula for the k plus first term of the sequence. And so we have a kind of a algebraic pattern that if it's true, it stays true for the next term of the sequence. And since it's true for the first term, and whenever it's true again, so by the principle of mathematical induction, a sub n equals 1 over n plus 1 for all n greater than or equal to 1. What makes this kind of a new problem for us is that instead of showing that two sort of formulas are equal, we're showing that the explicit formula for a sequence is equal to the recursively defined formula. Okay, hopefully you understand that. I think I explained that pretty well. Good, let's go to the last problem. Okay. And I think I did this on my answer key. I think I did this in kind of a confusing way. I actually haven't looked at this problem in over a year, but I think I will do it a clearer way maybe now than what I did on the packet. But this is kind of a hard problem. I think it's sort of fun. Maybe it's fun. Okay. Oh boy. Okay. There's a lot of sort of notation here. Oh man. Let's go. Number 55. Last problem of the sequences in series packet. Okay. Well, I got all these sequences. And, okay. In fact, in fancy people language, some people will refer to these sequences like this. Maybe that's not a good idea. I'll just write what's on the paper. We have all these sequences, so let's let A superscript 1 be the first arithmetic sequence, A2 be the second arithmetic sequence, A3 be the third one, A4 the fourth one, A5 the fifth one, etc. Okay, and will these go out until P? Okay, so I have P different sequences. Okay. Great. And they're all arithmetic. All arithmetic. Okay, well what do these sequences all look like? Well, they start with different things. The first one starts with 1, the second one starts with 2, the third one starts with 3, etc., all the way up to p. Okay, and also the common differences of these sequences are 1, 3, 5, 7, etc. Okay, so let me just write that down. So the first terms are respectively 1, 2, 3, 4, all the way up to p, and the common differences are 1, 3, 5. So in other words, the odd numbers all the way up to the pth odd number, and the pth odd number is of the form 2p minus 1. Plug in 1 here, you get 1, plug in 2, you get 3, so that's kind of like the general form for the pth odd number. Okay, and basically we want to just add these all up. We want to add up the first n terms of all of these arithmetic sequences. So, yeah, let's go. Okay, so what's p? P is just the number of different sequences I have. What's n? N is the nth term. So maybe I'll just write it over here. What we want is the sum of the first n terms of all the sequences. So we want the sum of the first n terms of the first sequence plus the sum of the first n terms of the second sequence plus the sum of the first n terms of the third sequence all the way up to the pth sequence. Okay, so how many terms do we have in total? Well, I have p sequences and I want n terms per sequence. So I have a total of, well, maybe this isn't important, but I have a total of p times n terms, which I'm going to be adding up, and I want to know what the answer is. All right, so this is just kind of a test to see if you can just handle all these kind of formulas. Let's see what we get. Let's make a picture of the first sequence. What does the first sequence look like? And maybe I'll actually just call it S sub n1. Because what is S sub n1? Is this what I want to do? Yeah, sure. Go over here. S sub n1 is going to be the sum of the first n terms of the first sequence. Well, what does the first sequence look like? Well, the first term of the first sequence is a 1, and the common difference of the first sequence is 1. So I think this is just going up by 1 every time. Yeah. So what am I adding? I'm adding 1 plus 2 plus 3 plus 4 plus all the way up to the last term is n. So it's just n. Alright, that was pretty easy. Should just not even look at what I have over there. Okay, what's the sum of the first n terms of the second sequence? Well, I think now this is maybe a little bit harder, right? Because what's the sum of the first n terms of the second sequence? Well, now the first term is a 2, and now the common difference is 3. So I skip by 3. So if I skip by 3, then that's 5, 8, 11, etc. All the way up till, well, what is the general form of the nth term now? It's going to be, well, I started with 2 and I added 3 n minus 1 times. So the nth term is going to be 2 plus 3 n minus 1. Yeah, that's just right. Okay. Looking good. Let's add up the sum of the first n terms in the third sequence. Well, the first term of the third sequence is 3, and the common difference in the third sequence is 5. So now I'm adding 5 each time. So 3 plus 8 plus 13 plus 18, etc. Moving up by 5 every single time. All right, I think I got this now. The first term is 3, and the nth term is going to be 5n minus 1. Okay, maybe I want to do one more, maybe I don't. Let's just do one more. The fourth, the sum of the first n terms of the fourth sequence. The first term of the fourth sequence is a 4, and we're skipping by 7, so that's 11, 18, 29, etc. Wait, yeah, no, sorry. Skipping by 7, right? So by 7, up by 25, great. And what we get is 4 plus 7n minus 1. Alright, and going all the way up to the pth, that should be an n, the sum of the first n terms of the pth sequence, which is, what's the first term of the pth sequence? Well, it's p. And what's the next term? Well, by the time I get to the final sequence, I'm skipping by whatever the pth odd number is. Okay, so I don't even really feel like doing this, but this is going to be, well, we're just going to add 2p minus 1 to p, basically. So maybe I'll even just write that as p plus 2p minus 1. And then, what's the next term? It's going to look like p plus 2p minus 1. And we're going to go all the way out till we hit the last term, which is going to be of the form p plus, the common difference is 2p minus 1. And now, by the time I get to the nth term of the sequence, I've added 2p minus 1 n minus 1 times. So this is the generic formula for the nth term of the sequence. Alright, and basically what I need to do is just add all of these up. I don't totally remember what to do, I just remember not to do what's on my paper. So I think I'm just going to do the common sense thing and just use the formula for the sum of the first n terms of an arithmetic sequence. What is that formula? Kind of off to the side here. The sum of the first n terms of an arithmetic sequence is n over 2 times 2a plus n minus 1d. Okay, so let's see, maybe I want to switch to a different color or something. I'm going to try to squeeze this in over here. Man, new board, but it's still not big enough. What happens when I add 1 plus 2 plus 3 plus 4 all the way up to n? Okay, I have a formula for that. It's n plus 1 over 2. But I want to kind of do this out in a more sort of generic way. So it's going to be n over 2, because I'm adding up n terms, times twice the first term, which is 1, plus n minus 1 times d, which is 1. Okay. What happens if I add up the first n terms in this second sequence? Well, now it's also n over 2 times twice the first term, which is 2, plus n minus 1 times d. And what is d now? It's 3. Okay. What about the sum of the first n terms in the third sequence? Well, it's going to be twice the first term, so twice 3, plus n minus 1 times the common difference, which is 5. And, alright, you know, with repetition comes understanding or something. Now this is going to be twice the first term, so twice 4, plus n minus 1 times d. d is now 7. And we keep on doing this until I get to the pth sequence, and the pth sequence, when you add up the first n terms, using the formula for the sum of the first n terms, is going to be twice the first term, which is p, plus n minus 1 times d, and d is 2p minus 1. Okay, and so, in other words, I just need to add all those purple things. And when I add all those purple things, what do I get? Well, every single one of them has an n over 2 in it. And every single one of them has a 2 times something in it. And okay, I mean, I think you can just kind of see this, right? And so what am I going to get? I think you're going to get n over 2 times a giant thing which looks like this. Trying to decide how much to skip, how many steps to skip. Well, I think you guys can handle this. It's going to be 2 times 1 plus 2 plus 3 plus 4 plus all the way up to p, plus factoring in n minus 1 out of what remains, I'm left with 1 plus 3 plus 5 plus 7 all the way up to 2p minus 1. Okay, I hope I didn't skip too much there, but I think it's pretty clear, right, that what I essentially did was to take all of, I mean, I just applied this formula, the formula we learned on, back already on November 1st or something, the formula for the sum of the first n terms of an arithmetic sequence, and I applied it p times to the p different sequences. And I got formulas which, when you factor out an n over 2, are all of the form 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4 plus all the way up to 2 times p. So I collected all those together and I factored a 2 out. I think that's pretty clear. And then the other half of the formula is that we're always multiplying n minus 1 times the first odd number times the second odd number, the third odd number, the fourth odd number, all the way up to the pth odd number. So all of these get connected together, and that becomes all of this. All right, I am now staring at a pretty straightforward algebraic expression. How am I going to do this now? Well, okay, I'm just sort of winging this, but I don't think it's too hard. What happens when I add up the numbers from 1 to p? Well, I just get p times p plus 1 over 2. That's just a fact. And what happens when I add up 1 plus 3 plus 5 plus 7 all the way up to 2p minus 1? That's p terms. And there's a bunch of ways to do this, but maybe we should just use the formula again, right? What is the formula for the sum of all the odd numbers? There's probably something smooth for that, but I guess is it just like p squared or something? It might just be p squared. Well, anyway, I'm not going to be cool or anything. I'm just going to do it because what is this? It's an arithmetic sequence, and so to find the formula for the sum of the first p terms of an arithmetic sequence, it's going to be p over 2 times twice the first term plus p minus 1d, and d is just 2. Okay, so what I mean by that is d is 2 because in this arithmetic sequence skips by 2 every single time, and okay, there it is. So, am I right about this? Does this just become p squared? Well, let's just do it out. So what do we get? We get p over 2 times 2a plus n minus 1d. Yeah, so I get 2p minus 2 plus 2. And so yeah, I'm totally right about that. So 2p minus 2, but then plus 2 just becomes 2p, and p over 2 times 2p just becomes p squared. That's kind of like a little just fact about what happens when you add up all the first p odd numbers. You just get p squared. Okay, I skipped a little bit of steps there, but I think you can figure that out. And okay, there was a bracket here, and these twos cancel, and so this whole thing now is kind of coming into shape. I have n over 2 times p plus 1 plus n minus 1 p squared. Did they give you the formula at the end? No, they didn't. What can I do? I guess I could just multiply this stuff out in the middle. I don't know what the best way to write out this final answer is, so I'll just kind of do whatever. So p squared plus p plus np squared minus p squared. And okay, the p squareds cancel, so that's really n over 2 times np squared plus p. And so maybe I'll just factor out a p and call it a day. So that's np over 2 times np plus 1. And that is the formula for the sums of all of these terms. The first n terms of all these sequences. Okay, was this problem fun? I don't know. Was it interesting? I'm not really sure. I'm not really sure if it was cool or important or anything. It is a good use of algebra and abstraction and kind of, I don't know, strategic formula using. So hopefully this made you 2% smarter. And that is the end of the packet. Goodbye.